We're going to change, I think, the level of discussion here a little bit. So far, we've been talking business strategy, the positioning of fog, some of the architectural issues that we're going to, the justifications for it, and so on and so forth. Today, not today, now, after lunch, après lunch, I want to talk a little bit about, it's a little bit lower level, it's a little closer to the implementation side of things, but it's still not implementation. This is kind of a vision, right? So one of our customers' biggest pain points, and I'm sure your customers' biggest pain points, is how do you deploy this stuff? How do you orchestrate it? How do you manage it once it's out there? If you have 50 billion endpoints, really, if this is a real number or more, trillion, I think Intel said trillion, right? That means every human being on the planet has to go out and plant 6 sensors at least, right? That's a deployment issue. That's a deployment nightmare. And then when you move it up a little bit into the fog, now the fog is doing real processing. How do you manage those? When a fog node goes down, do you send a truck out? How do you fix these things, right? How do you update them? So the software infrastructure that we have to put in place to make this fog rollout successful is significant, right? So today I'll talk about a little bit about this problem that we're talking about. And I'll focusing on cloud. Cloud already solved this problem, right? You can deploy tens of thousands of applications with a click of a button today on the cloud. So why not use their solutions, right? So I'll do a kind of a diff cloud fog. I'll show you the commonalities. I'll show you some of the differences. And then I'll conclude with a summary of what the infrastructure should look like, right, if we're going to make this successful. Now, I only have an hour. That means about 2.5 slides per minute. So I didn't have time. I'd say I'm covering about 40% of the problem today. There's it's not quite an iceberg, but there's a lot of stuff underwater. Okay, so in the introduction, I'll talk about defining fog. Just this morning, we've heard many definitions of fog, right? And they're all correct. I think edge computing it's all correct. But I want to narrow that scope just for this presentation. I'll talk about the problem, and then kind of summarize this vision that we have for how you control and deploy and orchestrate this stuff. Out of the many commonalities between fog and cloud, I've picked two. These two are key to everything, but there's a lot more commonalities. So it's not just limited to this, it's just a time limitation. And then the differences. Again, there's a lot of differences, right? I think everybody's run into them. These are 3 differences that are going to drive the change to how we do orchestration. But there's more. And then software infrastructure, there's a lot more than compute, storage, and network. There's analytics, there's databases, there's all these things that we're not going to cover today. I'll focus on these 3. And then we'll circle back to what it is that we need to do. So, I skipped the skipping. So at the end of the day, I want everybody to be on the same page, and I think we already are, just given this morning's discussion, that if we take the tools and services that work on the cloud and bring them down to fog, it's a big win for everybody. It's a big value for everybody. But it's not easy. We have to illustrate some of the gaps, and it's just some of the gaps, and then conclude with how close we are and how little work we have to do to get there. I thought this was a big font. This is going to be a problem, all right? Okay, so introduction. So let's talk about what fog is in this context, problem statement and the vision. So I think it's important to define the context, because even inside my very large corporation, there are conflicting views of what things constitute fog. And the reality is that you can put compute on a lot of different edge devices, right? All the way down from smarter things to capable, routers that have some leftover CPU there. And those are all legitimately called fog. We have vendors here who are implementing some of these things. We talked a little, Z talked about putting intelligence in the gateway, and that's a really good place to put intelligence. Cisco has some really capable cameras. These cameras have big old DSPs in them, right? And the customers want to put applications on there to do some signal analysis and so on and so forth. So that's a fog application. But that's not what I'm talking about today, right? It's an important part, and we have to, as an industry, deal with those parts, but today's topic is not that. Likewise, putting compute up in the routers and the switches and other appliances that are already out there is a critical part of fog. Because this is the cheap part. This stuff the customers have already bought, right? So we just have to enable it. It's a software problem. So to me, this is critical, very interesting, but again, not today's topic. How about on-premises data center? This is something that's always been there. Right? People have had compute on their premises the whole time, but now we have a name for it. It's called all-premises data centers. And if you put a fog application, a control application on there, right, and you connect that data center to a thing, then yeah, that's a fog application, right? So now we're starting to get to what it is that I do want to talk about. This is a new class of thing, right? We see some of these, as gateways get bigger, they start turning into one of these things. Or when you take what used to be a data center thing and pull it down on premises, or you put it in an attic in a building or something, it starts turning into one of these things. So for purposes of today's discussion, what I'm taking my definition hammer, and I'm defining fog to be this. It has to provide a decent impression of what a cloud server does today, right? I'm saying that that's the only thing that fog is. This is a thing that we're going to talk about today. Good. So definitions. If only it were that easy. Let's see what the problems are. Okay, so this is a traditional eye chart kind of topology, hierarchical diagram where you put the cloud up at the top. We have Cisco's huge core and some other players in here routing traffic around. And down here we have things. This is what's exploding. And we're defining a new level. Not defining, finding, somewhat defining. We like defining markets. So let's take a look at what IoT interaction looks like today, right? You have a phone, you have a Hue Philips light bulb or whatever. It talks to a gateway, maybe in your house, maybe in the building, maybe it's a microcell. That gateway turns that data, which could be Zigbee or some weird thing, into IP. The IP, we're really good at moving IP around, and we send it up to the data center. So the data center is today where a lot of these things happen. When you talk to your Siri or whatever, that's happening in the data center, right? When you go into a data center, what happens? These things are really well defined. There are whole industries here in Valley and out in the tech world that work at data center interconnect, right? So we're really good at it. And so when application designers design their applications, they know they're running somewhere safe. They're running inside the data center, right? And people who are outside the data center have to know that they have to get in there somehow. We need to keep that still in operation, right? There we go. So moving inside, what does a data center give you? First, nice big old walls. You put this data center out in the middle of the desert or in Norway up on a mountain somewhere, and it's secure. It's physically more secure than street lamps, right? Inside the data center, there's cages. The customers can pay for cages and locks, and we've seen some of those videos where you have to go through biometry and stuff to get in here. Another thing they do is big connectivity and really easy to change topology. So topology is sending a guy out, and he's going to unplug some wires from nice, capable servers and routers and put them into another wire. So these topologies are not just well-defined and well understood, but easy to change. Relatively easy to change. They still cost money to change. So we don't have data centers in the fog world, right? Because maybe these guys are all logically in the same group, but they're not surrounded by a wall, right? So what do we call this logical group of stuff? Is this a data center interconnect from fog to fog? Does that make this the gateway? Or what about this guy, right? And then when you're talking to a customer and they have on-premise DC, right? How do you say, well, no, you don't have fog, you have a data center, but we can turn it into fog. So we have to I guess my point here is there really isn't a defining wall. It's kind of, I don't want to use the word foggy, but it's hazy. It's smoggy, the difference between these two. So let's zoom in a little bit. It was an eye chart and still kind of is, unfortunately. All right, so when you start looking at some of these things, I already talked about some of these points. Let's zoom in a little bit more. Just for this slide, I call this a fog bank, but my boss sitting over here, Mr. Banks, is not so happy with that one. So, but we have to call this box something, right? What about, it used to be that every time you left the data center, you went through a firewall, a chunky firewall, a really capable firewall. Maybe some optimization, load balancing. Compression, IP compression is something that's very big now. So where does that happen in a fog node, right? You still have to, the application, the guy who wrote this, is assuming all that's happening, right? How do you implement that in a fog node? Does that mean that this fog node has to replicate every functionality that a data center provides? I'm not saying that I have a solution, I'm just saying that's a problem. Security, and we're gonna have a whole hour of security later, but this thing is sitting on a light pole or in a closet somewhere. Someone can go in there, plug wires. Who's a Spirent guy somewhere here? There's a Spirent guy who knows he can put a probe on these things and hack in, right? So we need to worry about security a lot more than the data center folks worry about security. And then finally, the whole point of fogs is you're talking to things, right? So how do you talk to things? Mud is sitting here watching me. That's actually a really critical part of how you design this, because the way people have designed cloud today, you don't talk to things. You talk to things through that IP barrier, right? We need to find a way to connect things physically to fog nodes, and manage that and apply policy and all. And we have a bunch of slides for that. Okay, so enough problem. Why are we going through all this trouble, right? We already have point solutions, right? Why are we doing this? That's an eye chart. Okay, so the vision is that once we extend, if we are able to make fog look like the cloud in terms of tool set, in terms of deployment models, in terms of the management infrastructure that millions of people have worked, not millions of people, hundreds of thousands of people like to work on. I think there's 200,000 Java programmers, and probably 190,000 of them working stuff like this. We want to leverage all that, right? That's the payoff. Don't reinvent everything. Right? How do we do that? So how did they do it? Right? How did this cloud infrastructure, which now powers the internet, how did that come about? Because 5 years ago, it wasn't, you said cloud, people didn't know what you were talking about. It started with hardware virtualization. So virtualization is an old technology, right? 1970s technology. It didn't become widespread until the big vendors, Intels and the AMDs and the ARMs, started putting technology into their ASICs that enabled this natively and with no performance impact. You could virtualize before. Fusion on Macs was running in 2001, 2002, but it was really slow. Now it's fast. Once that was there, hordes of programmers went ahead and started putting wrappers around it. Now here I only have Camus and KVM because that's what I like to use. But there's a lot of other technologies, Hyper-V, VMware, Zen, they're all there, right? And then wrapping those, there's, in my case, I put libvirt in there, but there's vSphere and all these other kind of wrapping technologies. They all assume that this core is there, right? Everybody uses the IOMU or whatever version of it you have. Everybody uses a VTX or whatever version of it you have underlying there. So it's built. It's a hierarchy of technology. Once that's there, right, then whole industries have sprung around orchestrating it. It's not enough to launch a VM. You have to hook it up to something. And then that something has to be a network that's hooked up to other things. And how do you measure, how do you charge for those things? There's a really large ecosystem of software. Now here I'm focusing on OpenStack because it's open, and I think it's a good candidate for what we're trying to do. But there are other technologies. There's proprietary technologies. There's vSphere, vCenter. There's Azure. There's Cisco has, of course, a few. And so we'll put those aside, and we'll just talk about this one big open one, which is really, today, is the only open solution that we have. Okay, so easy, right? You just take that stuff and leverage it. Once you leverage it, I pressed the wrong button. Once you leverage it, you get all this cool stuff for free. But it caught up to me, all right. But I kind of hand waved there, right? Frankly, these two parts here, the middle parts, the libvirt, the hardware virtualization, are fairly easy. You just have to go to the vendor and buy the right ASIC. Once you buy the right CPU, you get KEMU and KVM and all that stuff kind of for free, right? You may have to port a little bit, but it's fairly free. This stuff around it was built for the cloud. It wasn't built for anything. It's not as generic as, say, IOMMUs or SRLV. It's really built for the topologies that the cloud brings. So it's not written, unfortunately, it's not written for fog technology. It's almost there. Fog technology has enough differences that we're going to have to put some work into it. We're almost there. And then, so I'm going to go into the easy stuff first, which is where we have a commonality. Right? Now, some people, so I came into this thinking I would have to defend this idea, but what I've heard from the group is this is actually not a controversial idea. You have to support multiple tenants in these things. Now, multiple tenants can be multiple third-party tenants, or there could be the accounting team versus the security team, right, in one company. A tenant is just a different agency. And so I chose a real example. This is a public bus system, a fairly modern one. I only drew 3 cameras on this thing, but some of them have a lot more cameras, right? The things on this bus are the ECUs and the point of sale system, some driver lights, you're going too fast kind of thing. And then the connectivity out to the rest of the internet. Those wires up there, there's something like, I drew 3, there's more like 7, right? The way this works today is there's a rack behind the driver, right? It's a 17-inch rack where people just plug in their appliances, right? Which is great because we sell a lot with appliances. It makes, it's good for the DVR guys and the driver analysis guys. It's profitable. But it is a management nightmare and it's a policy nightmare too. Now, take a look at, for example, the ECU. The ECU is talking to something like 4 boxes. Right now, when you add a 5th box, someone has to go in there, change the programming, right? Say, okay, this box can see these parts of the ECU, but can't write back. So you have to kind of custom make policy, right? The integration job is just a nightmare. And something breaks. Okay, so actually, let's go to the pros and the cons. The pros are there's really good fault isolation, right? One of these boxes break, it won't pull down the rest of the boxes. And theoretically, each one of those boxes could be very good. And there could be a company that's extremely good at making DVRs, right? But in reality, they do the minimum they can, right? The cons are they're expensive to make, they're expensive to buy. Flipping, updating, changing one of these out is an expensive proposition. You have to go out to the bus and change it. And integration, every time you add a new application, it's a nightmare, right? You have to think about it for months because it's going to cost you a lot of money, right? And then the bonus con, I think we've seen it multiple times, is these agencies don't like each other, right? They're competing for budget. They're competing for space on the rack. So I think our first approach was, okay, you write one big application for everybody. And that was about 2 minutes of thinking before we said no. So you have to find a way to partition. And you know where I'm going, right? You take one very capable, fairly capable enough compute box. You pull all the applications in as virtual machines or other alternatives. And then you manage the connectivity and I'm going to stop using the laser because my battery light is flipping. So, but you manage connectivity, so on and so forth, in the inside software. You don't have to go out there and patch wires and so on and so forth. Okay, so management becomes much easier. Installation becomes much easier. Installation is actually launching a new VM. I mean, come on, you can't get it. Well, you still have to write the VM, but and there's things that today, like I said, there's a lot of resistance to doing new services because it's so hard to do. This enables a bunch of new services, right? Okay, the cons, I couldn't think of a con, so that's a joke. It's not really a con. Okay, let's take a closer look at that. I think the takeaway from here is the way that we share the way that we acquire, let's try to do the laser, the way that we acquire thing data is via a gateway. Typically you don't want applications accessing, we'll talk about this a little bit more, the things directly, because then they become less portable, hard to apply resources, and a policy. And when you want to share a resource like a camera, who gets to share, right? So I think the pattern that we see a lot is that the gateway is a virtual machine or an application that applies a policy and shares it out. That looks like the back of my desk at home, all those wires. But that's something that actually we manage really well, right? The cloud has a much, today their problem is much worse. They have tens of thousands of different tenants, right? And they manage to partition that data fairly well using overlays, software overlays. And so that's the approach that you would take here, right? You acquire the data via whatever protocol it is that that data comes in, you convert it into IP, and then you use overlays to distribute where it belongs. I only picked 2 of the applications here because otherwise a lot of colors. But you can see that the applications all kind of follow the same pattern, which is you collect the data somehow. And this data is only there, and you can only access it if you follow the right policy, or if you're allowed to by the policy. You do some processing, and then you share it on your private overlay. So your agency gets to see your data, nobody else. Right? This is critical. I mean, for a bus, it's not so critical, but if it's a security or a privacy issue, it's critical. All right. Okay, so that's my 2 easy ones. Here are the problems, and there's a lot more than just these 3 problems. These are the things where the delta is the biggest between fog applications and cloud applications. Topology is very different, and it has a big impact. Thing connectivity, connecting to things, and then because it's my favorite thing, is bounded latency and jitter, right? It actually imposes a lot of limitations on how you orchestrate stuff. Okay, so let's talk about topology. So when you have rows of servers, right, and you have a wire cage over them, and you have big routers, it's easy to set up whatever topology you want. Some researcher in Stanford will tell you this is the most efficient topology you can have for your application. You call the IT guy, a couple of days later, you have the topology that you want. Or if it's all SDN, even easier. You upload some new OpenFlow, and a couple months later of debug, you get what you want. So the problem is that the orchestration systems that we have today all make assumptions about the topology, right? It's not something that they really advertise. But when you say, okay, so the orchestrator in OpenStack is called Heat. Heat wants you to have this kind of topology. Like, here's a big router, here's some switches, here's some smaller switches, right? And it works best in that. And if you don't have that, you kind of have to map it to that somehow. Those orchestrators also assume that these pipes are very fat, 10 gig or multiple chunks of 1 gig, and redundant. Very, very reliable. And that these things here are very powerful too. So you can have routing tables in the tens or hundreds of thousands, or even bigger. So those are bad assumptions because that works in the cloud. It doesn't work on a little tiny fog box. And then you start looking at data-centric topologies like full meshes for Hadoop and so on and so forth. And to me, those are interesting because now the servers themselves have multiple endpoints. So A server usually has 1 or 2 plugs. These things have to have 6 plugs. And then I made the mistake of Wikipediaing data center topologies, and I found some really esoteric stuff. I don't even want to get into it. But it's a Google thing, right? But this is the kind of stuff you can do if you have a data center. You can go and say, wow, I ran some simulations. This topology works really well. Let's go implement it. In a fog, you can't do that because the fog is tied to the IoT, right? And the IoT is not so accommodating. If your data center is a city, like Manhattan, what do you do, right? You can't say, okay, let's go rewire all the wires in Manhattan. So what you wind up with is a kind of an ad hoc best fit topology where, man, that says traffic light, trust me. So you wire up what you can. There's some existing wires. There's some links that you'll have to establish or maybe pull wire from, very expensive. And you do what you can with what you have, right? That means that whatever your orchestration software is, it'll have to deal with amorphic topologies that are directly connected to things sometimes. Okay, and this is critical, this stuff here, I hate that, right? Because I go and measure my network's behavior, and I make decisions based on that, and then it rains, and your microwave channel goes down, or gets worse, you have to recalculate, right? So in the data center, that doesn't happen, right? The way they solve this in the data center, by the way, it does happen, right? Links fail, is, oh, that link might fail, I'll just do 8 links. And so you lose 15% of your performance for a little while until somebody goes and changes the NIC. You can't do that. You don't have that luxury. Another problem is connected to things. I don't think that this is strictly a data center issue. I think this is over the top of orchestration, right? But any orchestration system that you have has to take this into account, right? Today, cloud doesn't even know about things. These are little, meshes of things, right? And so when you spawn an application in the cloud, right, or a virtual machine in the cloud, there's really no way to say, by the way, that application has to be on this fog node that has these things attached to it. Those concepts don't exist. So how to add that is part of this discussion. What the applications do after they collect that information is, I think, over the top. It's a very interesting conversation. And you see a lot of industry, the IoT industry especially, has a lot of effort around this. How do you, let's go to the next slide so things actually become readable. Right, so you read these things directly. Now you're attaching things directly to a virtual machine or application. I like to use SRIOV because it's high performing, but there's other ways of doing it. And it's interesting that now these things usually aren't standard, right? These are bespoke devices, Zigbee, adapters and so on and so forth. And so you have to have specialized drivers for them inside the virtual machines. This stuff here, how you apply policy, how you distribute the data that you acquired from the things after you applied the policy, are, I think, beyond the scope of fog orchestration. They are thing orchestration, but they don't apply strictly to fog, they apply to things in general. So I'm going to kind of wave my hands and say that's somebody else's problem. It's a problem we need to solve. And I think there's a lot of money to be made there. Another thing that cloud orchestration has to do is find remote things, right, and connect them to the same thing. So we have to provide a way to put thing data in overlays and then distribute those to where they need to go. There's a special case, especially when you're talking about legacy applications. Legacy applications have already been written to talk to things, and they don't want to change. So we have to support those too. So when you tell your orchestrator, start this virtual machine, and that virtual machine happens to be a legacy application, you got to be able to tell it, and by the way, it's going to talk to this hardware, so it's got to go to this node. All right. Oh, I'm zooming through here pretty fast. How much time do I have? Okay. No, I'm good. I'm good. They'll have some time. Okay, so yeah, there will be questions, I'm sure. Okay, so, all right. This is actually one of, I think, the toughest problem that we have. It may be a problem that we solve later, right, because it's so hard. We talked about control loops. Control loops require a deterministic path between whatever you're sensing and whatever your actuators are. Now, the solution today is usually you put those sensors and actuators right next to each other. A robot, the thing that controls the arm has a little sensor on the arm, an optical sensor that knows the position of it. But that's not always going to be possible, right? In fact, we have to design for the case where that's not possible. So you have to assume that there's going to be a sensor network, say a windmill farm, where some of the sensors are over here. This is another windmill, and those are feeding up to this one, the control plane, controlling the blades on this third windmill. And you got to make sure that those are deterministic. You can't say, sometimes it's 10 milliseconds, but every 5 minutes, I schedule a new process, and it takes 30 seconds. Because then your windmill falls apart. It won't fall apart right away. It'll fall apart at the worst possible moment, right? So how do you do that? So here you have a control app. The orchestrator has to decide where, right? Where does it fit in this graph? That's, today in the cloud, that's a fairly trivial, there's a lot of research going around it, but a comparatively trivial problem. Because what you do is you look at network congestion and you look at server congestion and you say this is the least loaded server that's easily accessible, right? So it's a kind of a two-dimensional problem. I picked this graph deliberately. Between this node and this node, I drew at least 3 paths, and this guy only has 1 path. And this path is thicker, but it's through a kind of a dinky, smaller compute server. Maybe this is a router that has a compute blade on it, for example. And so now the orchestrator has to decide where does it go. So this I'm going to throw right out, right? Because this connection here is not guaranteed. It's non-deterministic. Data centers are also non-deterministic. They have to schedule you. They have to give you permission to run and so on and so forth. So if we could do this, then we could all go home. We're done, right? There's no reason for fog. Well, there's less reason for fog. There's a lot of other reasons. Okay, this is a good candidate, right? It's got a big old CPU. It can run our control application. It's got a fairly centralized location, so maybe a 2-hop between your sensors and your actuators. If you can guarantee that there's some determinism in this box itself, this is not bad. But I drew these lines thin on purpose. So if it turns out that you have a high bandwidth sensor kind of data flow, then that probably is not a good solution. Okay, so now here's this chunky 1 terabit switch that happens to have some leftover compute. So the connection is great, and because it's a 1 terabit switch, it's probably the connections are redundant, so you can trust them. But the application is probably a little bit too demanding, right? Control applications actually take a lot of CPU, right? And because it's just a tight loop. So maybe that's not a good candidate. If we could put it there, I think that's where I would put it. Maybe the solution is to buy a bigger router, and we'll sell you one. But assuming you can't do that, I mean, this is me talking through this decision making. Whatever algorithm is making this decision has to do it thousands of times, right? It has to do it optimally. All right, here we go. Now, I like this one because it has, if this path fails, then you have this path. If those 2 fail, then you have this path, right? So you have multipath. Now, that's great. A human can look at that and say, oh, that's a good idea. But a computer doesn't really know about multipath. It's really hard, right? It's a fit problem. So fit problems are hard to, for this simple topology, are probably simple, but for more complex topologies, computationally intense. And then one more place, this is something that typically is what happens today. You try to put it right near on a gateway, right? And some gateways will be able, like today, on the factory floor, this is where it goes. This is the OT approach. The OT approach is you have a SCADA controller, and that's where you put your application. So assuming that you can do that, good. All right. Now, Let's go back one. Now, this is something that really happens, right? Now, if you've been working with IoT for a while, you know that meshes often overlap. You design them so that they overlap because if you design them too far and there's a sensor in the middle, it won't connect to both. So often there's a sensor that can connect to this mesh or this mesh, right? And then something happens, somebody walks by and it loses a connection to one mesh and it winds up in another. So there is mobility in sensors. So all those decisions you made, assuming that your sensor would be over here, do you redo them? Or do you try to make, knowing that sensors will migrate, do you try to make a compromise decision? I could spend the rest of my career probably writing this algorithm, right? It's one of those, or you could just talk to some PhD and he'll do it overnight. Oh, that's NP blah, 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 and figure it out. Because I wrote a paper about that in '97. Okay, so boy, I skipped a lot of things, right? I'm looking at all the PhDs over here when I say that. When I skipped redundancy, right? Redundancy in data centers is solved very differently to how we can solve it. You just add more, right? And the connections are very thick and fat, and so I skipped security. I skipped all these things, and I wish I could talk more about them, but time. Okay, so how do we do this in OpenStack? OpenStack has 3 basic functionalities for this. In OpenStack, this compute thing is called Nova, and then over Nova, there's something called Heat. And what Nova does is, and in general, what you have to do when you're orchestrating compute, and what that means is deciding where your virtual machine goes, and then giving it the resources, is you find the resources, right, and then you allocate them. You find the image that you want to run, and you send it to the server. You apply some policy. Some applications can't run there, or if they can, they'll charge you more, right? So how you charge back and so on and so forth. You monitor them. Servers will go down. Not servers, well, servers do go down, but applications will hang, they'll go down. So you have to check heartbeats on all these virtual machines, make sure they're not stuck in an infinite loop. If they are, you kill them and you say, hey, you got to restart. And then you have to put them in the right place, given your policy constraints. So if you need a real-time box, it needs to go on something that can run real-time. So let's look at where we are on all of these. OpenStack does a lot of this already. Green stuff is what OpenStack does. In fact, some of those bullets I didn't even know about. I just went to the OpenStack capabilities page, and they were there. So all this stuff, caching, accounting, attesting that this virtual machine that you've asked for is a real virtual machine, the one that you asked for, is already, these are features that are already there. It doesn't know about things. So we have to do that part. Likewise, down here, OpenStack does the bulk of this already, right? It does monitoring, it does killing. This stuff, I mean, this doesn't even sound like a feature, right? But I put them all in that one ball so that I could just put a red circle around them, because none of this stuff is something that OpenStack does today. There are some things, RT, that OpenStack is working on, right? Deterministic execution of applications. But they're just starting. There's just blueprints at this point. They're not rolled out. Okay, so that I think, in general, we're not so far off here, right? Storage is something that we often overlook, I think, because it feels trivial. But application writers assume not just that they can write to a hard disk. They assume that they can write to distributed, redundant, secure storage, right? And so there has to be a service written around it. And there's 2 services in OpenStack today. One is, this would be Cinder, and this is, Swift? Swift. And they do a lot of the stuff that we need. They have some support for RAID. Block storage especially has support for local store. They are distributed if you want them to. It's a policy decision. And insofar as cloud computing goes, they are secure, right? They can encrypt. The problem is that they don't really think about people going into a server, ripping out a disk, and putting it in another computer. So we have to enhance it. If we want to use this service in the fog, we have to enhance security. Likewise, object storage is a really neat system that just about every serious application counts on, which is you don't store, you don't think you have a hard disk, you just think you have a file that you're going to put somewhere. And when you give a file to this guy via just a RESTful API, it'll take it and copy it 3 times or 5 times or whatever redundancy you want, and maintain those copies and maintain the consistency between them and so on. It's really kind of an elaborate system. In fact, that's part of where OpenStack came from. This was the rack space thing, and the previous one was NASA, right? So you can trust NASA. The problem is, they'll happily, of course, so security is a special issue here. When they distribute that data 3 ways redundantly for you, they don't encrypt it because encryption is expensive and because you're in a data center. Why would you encrypt anything? You can't really break into a data center. So that's a built-in assumption that we would have to fix. Dynamic scale, today they support dynamic scale. They support it in a very expensive way. We have to be frugal with our fog nodes, so we can't do it. We can't do it the same way. And then topology, they're just hopeless. They assume that everything is like what I talked about earlier, which is 1 or 2 hops away, very fat pipes. You don't care. The cost of talking to something across a data center is negligible. So we would have to, if we really wanted to enable this, we would have to be very careful in how we did topology awareness in Swift. Databases, I don't think, there's some database work in OpenStack, but I put it in there as green because there are a lot of open source databases that build on these guys that you can just download today. MySQL, NoSQL. Again, they all assume physical security, which is not guaranteed. You can't read that. It says streaming. So streaming databases are just kind of starting to come along in the cloud world. But for IoT, they're critical because a lot of the analytics you'll do at the fog level are on real-time data, right? So you'll be taking in 10,000 measurements per second and doing queries on those. If you try to do that on SQL, you'll need literally a data center, right? So you have to find an efficient way to do that. So that's a hole. Today, that's a hole. There are streaming databases, and they assume you have a data center, unfortunately. Okay, so that's not bad. We're almost there. One more. Networking. Now, more bubbles, because I work at Cisco, and I know networking. So I could do more bubbles. So there's really, I think, 3 big bubbles in networking. There's the data plane, how you implement the data plane. There's how you orchestrate, how you assign those data plane resources and connect them to the virtual machines. And then the services you built on top of that, right? And then there's a tiny little bubble up here called SLA, license service. What does SLA say? Yeah, it does. Service level agreements. And today, it's bandwidth, but in the future, we'll have to guarantee latency and jitter. Right, so today, when we talk about a data plane, we're really talking about, in the OpenStack world, open vSwitch, right, OVS. There are other things like OpenDaylight that build. I never know if I can say that it builds on top of it or under it or around it. It's all of the above. Yeah, it's a unholy matrimony. So those things are there. Now, I circled hardware acceleration. That's starting to come online. It's not really there. We know some vendors are doing smart NICs that accelerate OVS. Well, one thing it's not, QoS, yeah, I'll talk about QoS in a minute, is efficient. OVS is extremely inefficient. If you have an 8-core CPU running it, it's using half of those for any real bandwidth, right? You can run less bandwidth and so on and so forth and scale it down. But so it's very dependent on your application. That's why I made this circle big and thick, because we have to, as fog manufacturers, be frugal with our CPU. If we put out a fog box and we say, you're buying an 8-core i7 super powered thing, and it turns out that 6 of those cores are just moving data around, customers aren't going to be happy, right? They want 7 cores to move to do applications, and we can take maybe 1 or 2 cores. Okay, QoS is not really something that's central to, I think, what was the Google guy who said, the answer to QoS is just infinite bandwidth. So that's how you solve QoS, right? So it's not built into cloud. There are some, there's some blueprints that are kind of working around how you guarantee QoS using OVS, but they're not quite there yet. Likewise, oh, okay, so I did the red one first. Of course, latency and jitter is just foreign concepts to cloud, so we have to put those in. Okay, and the big problem here is that latency and jitter are dynamic attributes, right? So it's not just that you say, I found a fog node that has this latency and jitter, and I have to continuously measure and update. And then bandwidth. Bandwidth is actually fairly well supported in cloud stuff today. Orchestration, oh, 2 eyes. Can you even see those? You can't. No. All right, good. So provision. You have to provision these networks, these overlays, and connect things to the right place based on a policy. And then you have to account. You charge people back, right, for their connectivity. So that's fine. Now, today's orchestration doesn't know about the topology that we talked about. It doesn't know about, actually, it knows about a mobility. If you look at OpenStack and mobility, they are talking about mobility, but it's not the one that we're referring to. And dynamic behaviors of this stuff. Sorry, this stuff up here. So we're almost there. I mean, yeah, 50% there. And these things are all well understood. You can go to Cisco's website and download a cloud VPN if you wanted to do today, or you could risk one of the open source ones. But what's not there today is intelligent networks, right? Intelligent networking is the whole concept of measuring what your network's topology and behavior is and adapting to it dynamically. For cloud, that's a really nice to have. For fog, it's critical. So that's not bad. We're close. A lot of green. Okay, all right. 2 more slides, and then questions. Are we okay? We're okay. So this is a summary slide. I wanted to zoom out and show that really we're practically there, right? I don't want to downplay some of this red stuff, but if you took OpenStack today, you compiled it so that it was efficient, and you put it on a fog box, it would work. It would do 90% of what you needed to do. You would be able to manage that from afar. You'd be able to charge people for using it, deploy virtual machines. All that stuff is there. What's really missing is where and it's critical, right, is where fog adds value, right? So to enable the value add that fog brings, we need to work on these little red areas. So going back to the original thing, it's a pretty big footprint that we already have, right? And so what we need to do as an industry is take over the world, right? Now I left some, I don't do these lines arbitrarily. I left some things out. Like we were talking to a Hadoop company and trying to size what it would take to run Hadoop. Stuff like that, we really can't do in the fog. It's really something that belongs in a cloud or on-premise data center. And we're not going to run Netflix and Zynga, right? But we'll run our own applications. Once these services are available to end developers, right? In the same way that they're used to using today, we open up a whole ecosystem. Right? It's a call to arms. I mean, it's not something one company can do. It's an open thing. So we need help from everybody. And thanks. Questions?
I wanted to kind of conceptualize and say something what you have presented. You literally hit that nail right on that head, quite a few of them. people ask us, and so many of you guys here too, is that it looks very nice in a theory or paper. How do you put it into practice? One of the things that I'm looking at as a challenge, that you can put all those things that you mentioned, 90% up to a certain point, you can bring it to it. There's two markets. One is consumer market, another one is enterprise market. Enterprise market is pretty much static, that you can create orchestration, you can code in JSON, YAML, and cut through your Neutron, and SROV, you can deploy it. It will be there. Your code is static. You hold on to it for a certain time. Devices that we are majorly right now looking at coming in the market are more of appliances, handheld, useful device that will create a revolution in the market. Mm-hmm. And those devices are changing rapidly. I was talking to John earlier that you put your gateway, you put your deployment strategy inside of the gateway as a private cloud or some small device with compute, network, and control. But those devices got to talk to your back inside perimeter, but you have to code them. Mm-hmm. The challenge is that if there is a standard in between, which is, I would say, a fog standard, mm-hmm. that all these devices has to come and comply with it. So you literally write your REST APIs for those standards. You don't have to do any coding for each individual items coming into. So you literally have the vendor comply with the standard, and you literally hold on to your codes for your backend system. Consortiums are there. You guys, Cisco is one of the partners in the consortium, can push it and make it happen.
So we want to be careful conflating IoT standards with fog. There really aren't fog standards today. We have something called edge computing. And you have the IoT's computing model, right? But it's not the same thing as fog. Fog encompasses that and enables that, but it is not limited to that. In terms of deploying applications in a standard way on gateways, on consumer gateways and so on and so forth, you don't need the whole thing that I showed, right? Those consumer gateways are usually running Linux, right? And if they have the right hardware underlying them, it doesn't take much to start, probably not a virtual machine. These things are very tiny, but a container, right? And you containerize that application, or you have something running Java or Python, something in a virtual machine. In a Java virtual machine, not a virtual machine. Odd.
Coming at you. Sorry, Joe.
Yeah, so it's kind of interesting to see OpenStack being repurposed in the fog environment. Hadn't thought about it this way. So how does this work with IOX? And they parallel competing, or what's the story?
Okay, so I didn't emphasize IOX. IOX is Cisco's umbrella term for this kind. IOX encompasses everything from the APIs for talking to the hardware all the way through the application management layer, which is beyond orchestration. And orchestration in the middle. Now, it will interplay because we're using relatively the same APIs. And we're working closely with the IoTG team to make sure that we're on the same page there. But really, there's a lot of parallelism. Now, this is a fog computing thing, not a Cisco thing, so I didn't want to emphasize IOX. It's there, and it's a real thing. No?
Okay, I've got a question now.
Go for it.
Okay, so there's been a cloud in this room that's overhanging me, okay? And it's all this SDN, NFV stuff. So
those are two different things, right? Go ahead. Actually, I'll let you ask your
question. Well, no, just help me understand as I have advocates who are telling me that we're going to do everything end to end. Okay, even though, over on the other side, I've got this WebRTC event where in Cisco and Google's wildest imagination, I didn't think that session controllers would be the #1 deployer of WebRTC. So, end-to-end doesn't seem to be real. So, kind of tell me, you know, do you see these things interfacing to the fog? Do you see it as being totally separate? How do you see it all happening?
So I think NFVs are a critical part of fog. I showed one very quick slide there where you have virtual appliances in there because you have to pretend to be a data center. And that's how you do it. You have some NFV. A lot of NFV solutions today are very heavyweight, right? So that'll be hard to squeeze into a fog box. In terms of SDN, that is really application specific, right? If you look how people actually use SDN, they set up one thing. They set up, oh, I'm going to install my L2 switch on OpenFlow. And so that's not really SDN, right? SDN, if you really want to leverage it, you got to go to the researchers and the people who actually, okay, I'll do an L2.7 switch in OpenFlow. Further complicating things is OpenFlow 2.0, which is not really defined yet, but there's a lot of people racing towards defining it. So if you put a lot of effort into doing OpenFlow 1.3, which is really what SDN is today, that may go away, right? So I think a lot of people are waiting and seeing what's happening in that.
Okay. Hold on 1 second. We've got time for one last question. Who in the audience wants to be it? Ah, everybody's quiet. Give them a round of applause.